In this video, I will introduce you to differential equations, what they are, why they're useful, and how they're different than any of the math you've done so far. After that, I'll get you started on your first differential equation using a fun and intuitive dice game that doesn't need more than pre-algebra to understand. So let's get into it. So many times when we want to make a model of something, it might be difficult, if not impossible, to make a direct measurement of it. Or sometimes if we can, we might just not be able to figure out what function fits that behavior. In these cases, we may have some luck by looking at how the behavior is changing, or even how that change is changing, and then try to make a model that relates those things instead. When we create representations of functions like this, that is, a function in terms of its relationship with its derivatives, we're making what's called a differential equation. We can then manipulate and solve this equation for the behavior we're after. Now, although differential equations are often used for things that we have difficulty modeling, that's not always the case. For example, we could just take the sine function. Let's say f of x is equal to sine of x, and then its derivative f prime of x is equal to cosine of x, and then its second derivative f double prime of x is equal to negative sine of x. But f of x is equal to sine of x. So we could substitute the symbol f of x for sine of x in the equation f double prime of x is equal to negative sine of x to give us f double prime of x is equal to negative f of x. Moving the f of x to the other side, we get f double prime of x plus f of x is equal to 0. Believe it or not, that's a differential equation. And it's definitely not the one that we're going to derive later. Generally, it's not helpful to take an equation you already know and then convert it into a differential equation. Because if that was helpful, then there would be no need for the differential equation since we're usually using it to solve something we don't know. So how are differential equations different than the math you've done so far? Although you may know algebra can't model a dynamic system, you might be thinking the calculus you've learned can. In a way, you're right. However, up until now, the math you've done is in terms of elementary functions. Those are the functions like polynomials, trig functions like we just saw, and logarithms and so on. Unfortunately, the reason that we're unable to make good guesses most of the time about the behavior of a function that we're looking at is that those behaviors are almost never in a combination of any of the elementary functions. So we could combine them as we wish, but we'll never be able to replicate the behavior we're seeing. Also, the calculus you learn is focused on procedures like the chain rule, the product rule, and so on, but not on creating math models. In that regard, there's some good news and bad news. The good news is, whether you're a C student or A student, it doesn't matter. And it doesn't matter because most of the stuff you've learned cannot be used to solve a real-life problem. But that's about to change. No matter who you are or what you do, you could benefit greatly from learning how to take your observations about the world and put them in a format that allows you to make predictions about the future. And you don't know it yet, but deep within you, you already know a lot about differential equations. You've just never written it down before. But by the end of this video, you'll have created and understood your first differential equation. So let's get into it.
Dice 'em down! The game where you get either 60 or 10 dice, either 20 or 8 tries, betting either 1 or a $5 minimum. The rules are simple. Before each try, pick a number between 1 and 6. After the dice are rolled, dice matching your number are taken away. You get to pick another number and try again. If you get your dice count down to 1, you get twice your bet. If you get the count down to 0, you get 4 times your bet. So take those wallets out and get ready to play Dice 'em Down!
Okay, don't take out your wallet. Not yet. So there's a lot to unpack here, but let's not get confused by the options. Clearly, the game is trying to push us towards option 2 with 10 dice and 8 tries, but we're going to ignore that for now. we're going to go ahead and take a look at what we expect to happen when we play this game. Then we're going to play the game and then compare the results between our expectations and the reality. So, what do we expect to happen? Let's just pretend we have 1. We roll it and we pick any number 1 through 6, and that number has a 1 in 6 shot of showing up. So if we have 6 dice and we roll them and we're looking for a 2, each die has a 1 in 6 shot of being a 2. 1 in 6 plus 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 1 in 6. That should be 6 out of 6. That should be 1. So theoretically, there is a 100% chance that a 2 will show up. Of course, that's if everything obeyed those rules exactly. As we know, that's not how reality works. But that's the best guess we can get. So let's say we played the game with these 60 dice. What do we expect? 60 multiplied by 1 over 6 is 10. So we expect 10 dice to come up with that 2 or that 1 or whatever. Of course, that won't be the case exactly, but on a large scale, we expect that to kind of be the trend. And because we're taking the dice away, we could go ahead and say that we're subtracting that. So let's say negative 10. So to write that into a formula, we would say that the change in the amount of dice is equal to the amount of dice times a negative 1, because we're decreasing, times the probability of each die coming up that number. You don't know it yet, but we've just set up our first differential equation. Yes, it was vague. Yes, it was obvious. And that's the point. We can take vague statements about what we're looking at and transform them into very specific formulas. And I'm not talking what we just did. I'm talking what we're about to do. So let's go ahead. In order to get this in a manner in which we could manipulate it, we need to apply a little bit of notation to form it into an equation that we could easily manipulate and solve. First, let's look at the change section. We're saying that the change in the dice is equal to negative 1 over 6 multiplied by the amount of dice. But what is that change related to? What is it being measured by? It's the change per try. So let's write that out. Let's write delta y, the change in y, the dice count, per the change in try, right? We're trying again. So let's say delta y over delta t. And that's equal to y, our dice count, multiplied by p, our probability of 1 over 6, multiplied by a negative 1 because it's going to drop that amount. This looks a lot like a differential equation we can solve. There's only one little thing that we need to do. Let's look at that slope, the delta y over delta t. That looks, of course, like rise over run, and we know that the slope is interpreted as a derivative. But in this case, we're looking at a slope for something that is not a continuous function because we could only try in discrete steps. But if we look at this equation and imagine that we can make it a continuous function and that each try could get all the way down to a very small amount, like 0, we could use the tools of calculus to then manipulate it and solve it. So now that we have our completed differential equation, dy dt is equal to negative p times y, how do we solve that? Well, in order to solve that, we're going to have to do something you were told you could never do. And that's going to have to wait until next time.
Okay, now's the time to take those wallets out for real. Head to mymerchoutlet.com where you could get all the things you need. mymerchoutlet.com